I'm going to discuss a very important topic of grade 12 physics, and this is from topic chapter ray optics, and topic is refraction. And here we are going to discuss about a case where an object is inside a denser medium, like this is a small bulb which is emitting light in all directions, and this bulb is actually inside the water, and this is the surface, and above the surface we have air. And very shortly I'm going to show you the position of the observer as well. So this is the first case in which I'm going to relate a real depth, apparent depth with the refractive index of both the mediums. Now this calculation is done with one thing in our mind, that all the angles which are considered over here, all angles are small. So when all angles are small, sine theta is equal to tan theta is equal to approximately theta in radians. Right, people? Okay. So now let's begin. So here we have an bulb which is emitting light in all directions, but I'm going to consider two light rays, one which is directly heading onto the surface like this, and another ray of light going like this. Now the ray of light are going to bend away from the normal when they strike the surface. So this is the surface, this is the normal, and here this itself is on the normal. So angle of incidence is 0, and anyhow if a ray strikes the medium at an angle of 90 degree, it will go straight without any kind of bending. But of course there will be a change in the speed, right? Okay, and here we know that the rays are going to bend away from the normal. So the ray is going to bend like this, away from the normal. Now I'm going to assume an observer somewhere over here like this, and this observer is in the air. Now just imagine that our eye and brain, they do not understand refraction. So we don't understand that this light ray is actually coming from here. So our brain assumes that this light ray comes somewhere from here. So we feel the image of the object over here. So this is the image and this is the object O. Now this object is below the surface of water, and we have named the topic as depth, and we know that depth is always measured from the surface. So that means this is the real depth, that is HO. So HO is the real depth below which the real object is situated, where we see the image of the object over here. So that means this will be apparent depth HI. Correct, people? So our eye doesn't understand, our brain doesn't understand that this ray is actually a refracted ray and coming from here. Our brain and our eye feels that this ray is coming from an object which is situated over here. So actually if you look carefully, the real object is below, very much below the surface of the water, but we still feel the image to be raised up. So this is a virtual image. There is nothing sort of the object over here. We feel the presence of this object over here. So there is nothing actually over here, right, people? Now we know that this is the angle of incidence I, this is the angle of refraction R. Now I'm going to make all the angles like if you look at this, then here there is a Z formation. That means this angle, here there is a Z formation, and this angle are equal because they are alternate angles. And if you look carefully, if this angle is R, then this whole angle is R because they are vertically opposite angles. And here again Z formation takes place like this. So here if this angle is R, then this angle is also R, people. And I am going to mark this distance as X. Correct? Okay. Now what is HI and HO? Let me write it down. So HI is the apparent depth, whereas HO is the real depth. Correct, people? Okay. Now let me tell you how to write the refractive indexes. Just remember one thing in the entire ray optics chapter. You just remember one thing, that wherever you find the incident ray, that medium will be referred as medium number 1 and its refractive index should be taken as eta 1. Now, wherever you find refracted ray, that medium is medium number 2 and its refractive index is referred to as mu 2 or eta 2. And here we know that eta 1 is greater than eta 2 because this is denser medium and this is rarer medium. The optical density of this is more than the optical density of this. Now, let me take two triangles, this triangle and this bigger triangle. So these two triangles will be helpful for us in taking the relationship or obtaining the relationship between HI, HO and eta 1 and eta 2. Now let me write down the Snell's law for this surface. Snell's law is always applied on the surface where refraction takes place. So here I am going to apply the Snell's law. So eta 1 sine I, that is equal to eta 2 into sine R. So eta 1 sine I, that is equal to eta 2 sine R. Now all angles are small. If we are considering that all these angles I, R are very small, so you can take sine theta as tan theta as theta but in radians. Correct, people? So here instead of sine I am going to write down tan I, that is equal to eta 2 tan R. Okay. Now if you look at this triangle carefully, this bigger triangle, tan I is equal to perpendicular upon base. So tan I from this big triangle is equal to x upon HO. So here it is equal to eta 1 x upon HO, that is equal to eta 2. Now from this triangle, tan R from this triangle is equal to perpendicular upon base. So x upon HI, that is equal to x upon HI, and this x getting cancelled. So we get a relationship as HI upon HO, that is equal to eta 2 upon eta 1, where eta 2 is rarer medium and eta 1 is denser medium, people. Correct? So we have obtained a very important relationship, HI upon HO, that is equal to eta 2 upon eta 1, a very important relationship. And eta 2 is a medium in which we have refracted ray and eta 1 is a medium in which we have incident ray, right? And this is case 1 and I'll be continuing this case 2 where the object will be in the rarer medium and the observer will be in the denser medium.